So here we are at the MotoIQ Garage, in the middle of the COVID epidemic, and we were practicing safe social distancing while we're filming, and we're all masked up with our N95 masks. So in our last video, we built a 650 horsepower naturally aspirated LS3. This was a pretty simple engine, really built for reliability, not peak horsepower. And now we wanted to do something more exotic. This is a 1400 horsepower LS-based engine for Formula Drift competition. If you didn't know, Formula Drift is one of the most brutal, abusive engine environments in all of motorsports. Probably the only thing I can think of that's more abusive is offshore powerboat racing. In drifting, you're running for about a minute a run. You're running all day. You're going from maximum RPM, maximum load. You're clutch kicking, violent RPM fluctuations. It's really hard in the entire motor, especially the valvetrain. I know in our last video, some of the comments were things like, oh, I get 1600 horsepower from my stock bottom end LS3. Well, sure you can do that, but being a dyno queen, going for a blast down the street or an occasional blast down the quarter mile isn't actual motorsports, and it isn't for sure drifting. Our engine makes 1400 horsepower, and it can do it for an entire season of Formula Drift with no real maintenance, and we can do it all on one engine. So that's pretty, I guess it's pretty unusual. Most other teams probably go through at least one engine this season. Some teams go through almost one engine every event. So we're pretty proud of what this little LS does here. Now let's go look inside and we can show you what we did to help make this thing live under such bad conditions. So the heart of any really high horsepower engine is the block. And in the case of our engine, we didn't feel like the stock block was going to cut it, because for drifting you need a lot of power, a lot of torque, and a wide power band, and the best way to do that is displacement. So we built our engine to be 454 cubic inches, and then to enable that we use a RHS block. Now this RHS block deviates from your regular Chevy LS in a few ways. One of the ways is it has a really thick cylinder liner. We start off running the block at 4125, and you can bore this thing all the way out to 4165. So we could get a whole bunch of rebuild cycles out of it, and we can make the engine really big if we wanted to. Now, that's the first thing. The other thing is this block has a really thick deck compared to the stock Chevy blocks. So when you're running a lot of boost, it helps seal the head gasket. There's less flex, less opportunity to cause any kind of distortion with the studs, and helps to seal a lot. The other interesting thing is your standard LS has 4 bolts per cylinder to seal the head. The RHS block has 6. We have two here and 4 here. So you have way better clamp load down on each cylinder to help seal. That's a pretty big deal and really helps the head gasket live. Another really important thing is the RHS block has a taller deck. Now the deck is about an inch higher than stock. And what that allows us to do is to, we can run our stroker crank. We run a 4 1/4 inch stroker crank, and we can run a really long connecting rod. We run a 6-350 connecting rod. So our stroke to rod length ratio stays reasonable. Our piston speed stays reasonable, and the angularity inside the engine stays reasonable, so you don't have the piston digging into the cylinder walls. It helps wear, it helps volumetric efficiency a little bit, and your piston's dwelling at TDC longer, so you have more time for the combustion event to impinge on the piston, so it helps your thermal efficiency a little. It really helps with the mechanical stress on the engine, and if you even to hear our engine sounds a lot smoother and less thrashier than other big displacement LSs out there. Kind of sounds smooth, kind of like more like an Indy car than like maybe a NASCAR, for instance. A lot of that is the really long rod. The RHS block has plenty of room inside, and the cylinder liners are notched. This is so you can run up to like a 4/600 stroke. Like your stock LS blocks, once you get past 4.125, it starts to get iffy, and you have to clearance the block. But RHS block is actually wider in here quite a bit, so you can run that big stroke without any interference. The other thing is the RHS block, it moves the camshaft up higher. There's plenty of clearance for the stroke. You have to run a timing set with 2 extra links. It's 2 links worth of height. And then you can run shorter push rods, shorter, stiffer, and less flex in there with the higher cam. There's more windowing around each main buttress here. This gives you more windage volume area. And so when the pistons are pumping up and down and the air's blowing around, there's a lot of places where the air can exchange, and you reduce pumping losses that way. So after I guess the LS3, they opened up the windows on the factory blocks for that reason, and the RHS motor opens up the area even more. So you have a lot better internal air exchange and less pumping loss. Another cool thing is the RHS block has bigger registers on the block, where the main caps have more purchase to the block. This gives you more support. When you're running big power, everything is moving around, and we actually see when we're pushing more than in the 1400 horsepower range that the block actually starts to fret here, which means the whole block is flexing, and that's kind of means we're approaching the limit of the block under our abusive conditions. But the RHS block has a lot more register room than stock, and it's a lot stronger in this area. Another important feature you can't really see, but the RHS block has what you call a priority main oil system. What that means is when the oil comes off the pump, it goes directly to the main bearings, and the top end is lubricated from oil that bleeds off the mains, so you're getting full, complete pressure right to the mains first. Like on the stock LS, it goes into a galley, and the galley splits and feeds the main and the top end. So the main doesn't get the priority of the oil system. Well, the RHS, with priority mains, the mains are getting all your oil. So, for a performance engine, that's better. If you're running a dry sump and the roller cam, mechanical roller cam, you need to restrict oil to the top end. It's a lot easier to do it with priority mains to restrict the oil passages. It's a lot better. And most serious performance engines are lubricated that way. There's also spaces to put oil squirters for your pistons if you wanted to. We're not going to run squirters because we run ethanol on this engine, and piston temperature isn't so much of an issue. But we really like this RHS block, and it's a good solid foundation to make a lot of power for a long time. Another reason why we use the RHS block is it's made out of aluminum. Now they have other heavy-duty blocks with tall decks like the Chevy LSX, but the RHS block is about 80 pounds lighter. In a drift car, you don't want all that weight on the nose because handling is really important. And we're always trying to get close to 50-50 weight distribution, so 80 pounds is a good chunk of weight not to have on your nose. Now let's go look at the rest of the engine. Now we get to look at the insides of the engine. Probably the most important part for reliability of your engine is the crankshaft, and we didn't spare any expenses here. We used a Callis Ultra crankshaft. Now this crankshaft is totally badass. It's machined out of a billet of Timken 4330 alloy. Now this is a special alloy that's high nickel, high chromium, really tough, and it's vacuum degassed when they're making it. What that means is they get the metal, put it in the vacuum, and all the impurities kind of get sucked out of the metal. So there's like less porosity and less inclusions inside the metal to where a stress crack could start. Now this is pretty trick metal, and as far as my knowledge, Callis is one of the only ones that makes it in one of their cranks that you can just buy off the shelf. So you start with a really good metal. It's machined. You can see things like it has very generous fillets here. That's to reduce any kind of stress riser, and that makes a really big difference in the crank's durability. All the holes are chamfered and profiled right from the factory. You don't need to do it. It's a hollow crank pin, so the reciprocating weight's kept low. All the counterweights are profiled. They're knife edged and blunt trailing edge, so there's less windage. The crank spins around, has to spin through the oil cloud, so you want your counterweights to be aerodynamic, and these are all profiled. The whole crank is super finished, so it's nice and smooth. Less windage losses, less surface defects to where like a crack or something could start. That helps fatigue life too. The super finishing goes on to the journals, which helps your bearing life. It's a really neat crank. The crank is also internally balanced. You can see some of the weights here. And this is like a heavy metal. They call it Mallory metal. It's kind of like a tungsten alloy. So when they balance it, they figure out this weight, press it into the counterweights. That way the crank is really well balanced internally, so you don't have any additional stresses in the crank. It's a really expensive way to balance, but that's the best way. We get the crank and we give it a fine balance to match our reciprocating assembly exactly, and then we have the whole thing WPC treated. Now we talk about WPC a lot, but it's a Japanese super finishing process that's kind of like shot peening on a microscopic scale. It leaves a really fine compressed surface where that's hard for a crack to start in. Really helps your fatigue strength, and it's ultra low friction. The RA on the surface is lower than traditional super finishing, so it's a super smooth, super slick, really hard, thin surface finish that it's almost impossible for a crack to propagate in. So you reduce friction, you increase your life, and you increase your fatigue strength. And we WPC anything that can rub in an engine. Like on the block, we WPC the cylinder walls, we WPC the crank, pistons, rods, camshaft. We WPC the valve springs because that helps their fatigue strength. Anything that rotates or rubs on a really serious engine, we WPC. And we found that this actually helps life maybe about as much as 50%, sometimes 100%, depending on what the component is. Our valve springs don't fatigue nearly as fast. When you use a radical roller cam, you usually have to change your valve springs out like every few events, but with WPC, they last the whole season. Our bearings last the whole season. We don't even need to crack the engine, which is really unusual. So WPC is a great thing for life. It's supposed to give you more power due to reducing friction, but that's kind of hard to subjectively measure, and But we can tell things like when you assemble the engine and you're spinning it around, the torque to spin the engine is really low with WPC. So you can feel the friction reduction right there. So that's our crank. This is a really nice piece. One of the best cranks I think you can get on the market, like off the shelf. Now the crank spins in King bearings. We really like King bearings in a performance motor where everything's clean. The bearings are like a lot harder than your typical tri-metal bearings, so their load bearing capacity is higher. They have this PMAX black coating on there that's a nanoparticle. It's not your typical low friction coating. It's a nanoparticle with a lot of solids, and it actually helps the load capacity, and it's not just for run-in and not just for friction reduction, even though it does that. So these bearings are normally good for an entire season, and when we pull the motor apart, they look brand new. So next to the crank, the next important thing is the connecting rod. Now we use a Callis Ultra I-beam rod, which is their top-of-the-line strongest rod. Now, like the crank, the rod is made out of Timken 4330 vacuum degassed, high nickel, high chromium alloy. Super tough, proprietary alloy, vacuum degassed to eliminate internal voids and things that can cause fatigue crack starting sites. It has ARP custom-made 625 bolts, which are, like a step up from the typical ARP 2000. Really good bolts. The whole rod, every corner and every radius is rounded, so you don't have any place where a stress riser could start. I mean, this is a really nice rod. The rod is shot peened after it's finished. That helps improve the fatigue strength. It's a really nice piece, and it's actually like beautiful to look at. On top of everything that Callis does is we actually WPC the rod, and we cryo-treat it also. So the rod's cryogenically treated. The rod bolts are removed, and they're WPC treated and cryo-treated. Rod bolts are critical, so we don't want to have any kind of place where a fatigue crack could start. The rod bolts are the highest stress part of the rod, and if one of those fail, it usually takes out your whole engine. So we do a lot of TLC on the bolts. We also cryo-treat the crank, and actually we cryo-treat all the internal components of the engine. Cryo-treating is an extension of the heat treating process where you convert like your austenite and your ferrous metals into martensite, which is a harder face-centered cubic version of the metal. Now that's a lot more fatigue resistant, a lot more, your actual mechanical properties improve, like your tensile strength. It stress relieves the part, so it helps wear, improves strength, and helps fatigue strength. Now, cryo is a pretty interesting thing, and you need to know metallurgy to understand it, but believe us, we think it's worthwhile. So for pistons, we run a JE FSR piston. Now, this is a strut-type forging. It's a cut-down slipper skirt, but with the struts, like right here, you have a really good support of the pin boss, even though it's really inboard. The inboard boss gives good support of the piston pin, so you could have a short pin that's lightweight, and you could still have good support and good strength. The FSR has asymmetrical skirts. You can see that there. The thrust side is wider than the non-thrust side. That's because the thrust side is the side that gets dug into the cylinder wall and takes a lot of load. So it's wider, so you have more area. The non-thrust side is narrower, so the piston can be lighter there and have like less skirt friction. There's some cool features, like We're running low tension piston rings that are really thin. There's a pressure equalization groove in between the number 1 and number 2 ring that kind of helps the number 2 ring seal better. And there's this little step here. It's hard to see in the video, but that helps pressure get behind the number 1 ring and acts kind of like gas porting. Helps the seal on the low tension ring. Since we're running a long rod, the pin is way up, almost into the oil ring, as you can see. It's an 11-to-1 compression ratio. We're running that high of a compression on a turbo motor because we're running ethanol as fuel, so fuel octane is no problem. And the higher compression helps off boost response and helps spool the turbo quicker. The piston and the pin is WPC treated. We're running kind of a thick wall pin that's important with a turbo motor and any motor with high cylinder pressures because if your pin starts to flex, you spin the bushing out of the small end of the rod, and that usually results in things that aren't too cool by our experience. The pin is really high, so you can see how it's almost up into the oil ring because of our stroke to rod length ratio, and everything is WPC treated. That helps wear in the pin boss, helps the pin wear, and the most important thing, it helps the wear in the ring grooves. And the ring groove wear and the clearance of there is one of the things that helps give you good leak down and good leak down over the life of the engine. So if you can reduce wear, that's all good. So WPC really helps this out. Really neat piston. What else do I need to talk about? Oh yeah, this piston's made out of 2618 low silicon alloy, so it's a nice tough alloy that is ideally suited to turbo motors. Normally this alloy has to run really wide piston wall clearances because it expands a lot more than, let's say, a hypereutectic piston, but that's what you pay for the strength. JE has done some things to counter that, like they design a cam shape into the skirts, so they're not like exactly a cylinder, but it's kind of like a cam, which reduces your piston slap noise, and it allows you to run a tighter piston wall clearance than you normally would with this alloy. Now, on a naturally aspirated motor, you can run as tight as 3,000ths. We run it at about 4,000ths because the turbo motor puts a little more heat into the piston, but that's still really tight. Doesn't make any piston slap noise, and the cylinder wall and piston skirt life is still long, even with this alloy. So one of the key parts of the engine to make power is the cylinder head. Cylinder head has to flow good, number 1, and if you can get a good, efficient combustion chamber shape, that's number 2. So what separates the men from the boys in developing power is a good set of heads. Now, we start with the All-Pro cylinder head. The All-Pro head is perhaps the highest flowing LS head on the market, arguably. It's all new casting. Some of the cool things about it is it has like a really thick, 3/4 inch thick deck. So no flex, even with boost pressure, and you don't have to run too exotic of a head gasket. When you compare between the deck of the block, the thick deck, and the thick deck here, you get a lot of good clamp. It's 6-bolt compatible instead of 4, so you get more even clamping pressure around each cylinder. The ports are tremendous. Like the intake and exhaust ports are huge. They're CNC finished. The intake port has a little fin in here that goes to the valve guide that helps swirl into the cylinder. These heads flow a lot. Like it's way over 400 CFM on the intake. It's about 420 CFM in our motor, and it's more than 260 CFM on the exhaust. Last time I looked, these flowed the most out of any of the aftermarket LS heads. The valve size is pretty big. Like the intake is 2.25 inch. Now that's up from the stock LS is 2.2 inches, and the exhaust valve is 1625, and the stock LS7 size is 1610. So the valves are bigger than the LS7. The combustion chamber is shallower and has more quench. So you have your quench pads here and here, and really shallow. Like a shallow chamber has like less surface to volume ratio, so it's more thermally efficient. You don't bleed heat into your water jacket. You bleed, your heat stays in the chamber and helps drive the piston down. A flat chamber, small volume is also good. Like you don't get as much detonation that way. The quench area is the flat areas here that are really close proximity to the piston at top dead center. And what they do is they squish the unburned fuel air mixture from the edges of the cylinder where they don't do too much toward the spark plug. So that helps have a turbulent combustion chamber, good homogeneous mixing, and good combustion. When you have a good set of heads, you don't need to run as much timing. And we noticed that to be true in this motor. This motor really doesn't like more than 25 degrees total advance, even when it's going full tilt. And a lot of that, when you start advancing the timing more than that, the power actually goes down. And a lot of that's because of these really efficient heads. The valve stem diameters are a little thinner, so less impedance to flow. Here's our valves. We run a stainless steel intake. We don't run titanium because titanium's abrasive and tends to wear out your valve guides. Even if you have coatings and anodizing and stuff, they're still kind of abrasive. And we found that titanium doesn't have the fatigue life, and like it beats up the valve seat, and the keeper groove wears out, and it's kind of a high maintenance item. So we run a regular stainless. You can see it's a flathead profile here. This helps flow on the intake side. The stem is reduced in the area of where the flow goes around that's not around the valve guide. That actually makes a pretty big difference in flow, like maybe 10% increase just by reducing this diameter. We WPC treat the stem and everything, which on the roller cam with a lot of side load helps the life. The exhaust valve, we use an Inconel valve. Now Inconel is a super alloy that's really good at taking heat. It lasts a long time. It doesn't sink. It's a really good heat sink. Pulls heat out of the head of the valve. You can see that the exhaust valve has kind of a tulip contour because the flow is going the other way. So this tulip actually helps the flow coming out of the cylinder. It has a reduced stem like the intake valve, and of course we WPC treated it. A real quick thing, one of the interesting things is when you have a tall deck block, your heads are kind of farther apart. And to be able to run a regular intake manifold from an LS, we run these adapter spacers from RHS. You put these on the cylinder head and you can run any LS intake manifold with no problem. Drifting is really hard on an engine's valve train. It's violent fluctuations in RPM. The engine can even spin backwards sometimes if the car spins out wrong. There's clutch kicking. All kinds of things going on, bouncing off the rev limiter. So it's perhaps the hardest thing on the valve train out of any motorsport. And a lot of the most critical part is the camshaft. Now we use a mechanical roller cam. Hydraulic cams don't work too good in drifting, even like a low lift hydraulic, because they tend to start to pump up when you do all this crazy RPM fluctuation and you lose control of your valve motion, and all kind of bad things can happen. So even the high performance, low lash hydraulic roller lifter doesn't work too good in this case. So the cam we use is custom made for us by Comp Cams. Now, I worked with their engineers to develop a lobe profile, especially for a turbocharged drift engine. Now, this isn't really designed for the ultimate in power, but it's designed to make the best power, to be durable, and to be stable under the conditions of drifting. So it doesn't have super crazy lift or duration. It does have pretty radical valve motion compared to something that's stock. I mean, you can kind of see like how the lobes are, but it has like an inverted flank on the opening side. The profile is asymmetric, so it's kind of like faster opening, slower closing. You want to do this so you don't excite the valve train and cause surge at certain harmonics. Like surge is, I guess, engineering for valve float, and it starts to get problematic at higher order harmonics, like maybe 5th and 6th order harmonics, where like the little forces build up and can cause the valve train to start to float actually. So Comp used their latest profiles and technology with computer simulation and spintron testing, came up with this lobe profile that does not excite the valve train as much. To accommodate the turbo motor, we did some things like we spread the lobe centers more than typical. You don't want to run a tight lobe center on the turbo motor because you basically blow the boost out the exhaust port. And you can get reversion too at lower RPMs where the hot exhaust can actually backflow into the engine, and that's not too good. We also kept the duration split between the intake and exhaust kind of low compared to what works on a naturally aspirated LS. Some of it's secret, I'm not going to tell you, but Comp was very cool about, like helping us and giving a lot of technical support and sharing some of their latest profile information with us. So it's a custom Comp cam. If you're a serious racer, Comp will work with you to develop your own profiles too. They're very helpful, quick turnaround. Pretty amazed with the service, and like everything else that rubs, the cam is WPC treated for all the friction reduction and wear increasing reasons. That's kind of like this lustrous finish you see on it. We're really eager to give this cam a try. It should work really well. For the rest of the valve train, for the springs, we use prower double springs and with a damper. The damper kind of helps with spring surge. It's like kind of like a shock absorber, but it's a friction damper that goes between the inner and the outer. It kind of is way different pitch and everything. So your inner is going to have a harmonic, the outer is going to have a harmonic, and this is going to have a way different harmonics. So it acts like the friction damper, and it's not all going to resonate at the same RPM. So that's the idea. It kind of helps break up that surge. We're running prower titanium retainers. Everything is cryogenically treated and WPC'd. The cryo treating, we explained it a little earlier, helps fatigue life. So does the WPC. Normally when we don't do this, the valve springs last maybe 3-4 events before they get fatigued and need to be replaced. But with WPC and cryo, they easily last the whole season. And we've even pushed a set 2 seasons in an emergency, which is kind of unheard of with a mechanical racing valve train. Now, we totally don't recommend this, but it was an emergency, so we kind of had to just keep the same valve springs in the motor, and with the tempo and the transportation time, we weren't able to change them. And anyone that does pro motorsports, you don't have a multi-million-dollar budget and tons of spares, has probably been in that kind of situation before. If you have to push your parts longer than they're intended to run, cryo and WPC is a really great thing. One of the key things to assure your engine life, if it's a competition engine, that really gets ignored is the oil pump. Now your stock oil pump is probably good for your typical hard use. You can do some track days, some drag racing, but when you get into big power and a serious car that pulls more than 1G for a very long time, like a car with slicks that does serious wheelie popping launches, like a circle track car that does G's in one direction for a really long time, or a drift car where we see as much as 2.2 G's on the bank track. Your regular wet sump system doesn't cut it. And one of the things that we found that really helps life is a dry sump system. Now the dry sump has all kinds of advantages. Our dry sump system is daily engineering. I like to run this because everything is all integrated. The pump and the bracket and everything is integrated into the pan, so it's very clean. Lets things to vibrate loose. The pan is like a nice thick piece of billet. The pan actually kind of encloses the bottom of the block and kind of helps keep the bottom end from flexing. So the pan actually helps the structural integrity of the bottom end. You can see how the pan this kind of comes down around the main caps here. That helps to make sure each stage of the dry sump, you can kind of see the screen slot here. The crank's spinning around this way and it flings oil into the slot. This is a 6-stage dry sump. So there's 4 suction stages, 1 suction stage for each crank bay. So you have one little gear rotor pump sucking all the windage cloud and everything out of each section. Now this helps reduce windage losses, so there's very little oil, air, mist flying around in here. All the oil gets sucked in. So your crank and rods and everything are spinning, and there's not much like oil around in there, and that helps reduce windage losses, so that increases power. The dry sump kind of runs a slight vacuum in the crankcase, so your piston rings seal better. The dry sump actually gives you anywhere from like 10 to 20 more horsepower for this reason. It sucks every bit of oil out, and because of the active suction, it doesn't matter how many G's you're pulling. If the car is upside down, it'll still suck the oil out. You could be pulling like 4 G's in the ground effects car, and it'll still get you oil. Like it sucks it all out. Goes to this multi-stage pump. Here's your 4 scavenge stages that suck out of each of the crank bays here. There's 2 pressure stages that feed your engine. One goes to the tank and one goes from the tank to your engine. The tank itself isn't here, it's in the car, but it's a big 2-gallon unit, and it has filters, screens. It de-aerates all the oil, gets all the air out. One of the things about a wet sump is the crank and everything's thrashing around, and it's whipping your oil up into a froth, and then your wet sump is picking it up, and even if you have a windage tray and baffles, your oil is still pretty aerated. So I'll use whipped cream as an analogy. I mean, it's not that bad. It's sort of like, I don't know. In the wet sump, you have like, up to about 40% entrapped air in the oil. And your lubrication ability of your oil goes really down once your entrapped air percentage gets past like 15%. So you're pumping frothy oil through your engine that doesn't lubricate versus solid de-aerated oil under high pressure with your dry sump system. So your dry sump gives you good lubrication, solid non-aerated oil, and gives you lubrication no matter what the G-force is. So it's expensive, but it pays off in engine life. Totally worth it. So a lot like what goes on in the drift engine is keeping the valve train alive. And because of that, we didn't want to spare any expense. Now, in drift engines, we have the best luck with prower shaft rockers. Now, these are roller rockers mounted on a shaft. The rocker body itself is stainless steel. The shaft rocker is good because the roller bearings, the rocker can't spin sideways like it can with like stock type rockers. So there's no skidding off the valve tip. When it's on the shaft, the forces involved with going up and down and compressing the springs is spread out over this bigger area instead of just the fulcrum. And what happens on a lot of these big LSs is the pedestal for the rocker starts to crack into the intake port. And then, that's not good. It's a big vacuum leak and everything screws up. These All-Pro heads are kind of beefier in this area than like a stock, like let's say an LS7 head, but it's still better to spread that load out so you don't have any risk of cracking your intake port. And we've seen the intake ports crack a lot with pedestal style rockers. So the shaft rockers won't let it spin and spreads out the load, and both of those are great reasons on the drift engine. We're talking about double valve springs with dampers and titanium retainers. You can see that here. We use a big 7/16 push rod. You want to have a big push rod so you don't have flex and you have accurate valve motion in one of these engines. To run a big push rod, we have to have what you call offset lifter cups. So they actually, where the lifter goes into the push rod goes in the lifter is actually offset, so the lifter itself doesn't rub inside the head. So that's kind of like a special order item that a lot of people don't realize about. These are mechanical roller lifters with a pressure fed roller. Now, like some of your cheaper lifters don't have a pressure fed roller, and we found that those don't last very long in the drift motors. So pressure fed rollers are really important. Everything is prower. The push rods are seamless, heat treated, machined ends or forged ends, really strong stuff. Most of the engine failures we see start with valvetrain failures, so you don't want to skimp here. So here's the bottom end. You can see the RHS billet main caps, and they're held in with ARP studs from 6 directions. There's 4 on either side of the crank, and there's 2 to connect it to the side of the block. Now this is about as strong and stiff as it gets. The registers are bigger and have more surface area than your stock Chevy ones, which kind of helps the clamp and the stiffness. Really strong part of the motor. But drifting is so violent that we actually see some fretting here and there toward the end of the season, and we have to align more of the block. That's how brutal, the loads you see in drifting, and it's pretty amazing that a motor that's this heavy duty can still show signs of abuse. You could kind of see the aerodynamic profile of the callus crank a little better here. You can see the 625 custom age rod bolts. When we torque the rod bolts, we use stretch instead of torque. That's the most accurate way to do it to get the best fatigue life. Another tip that if you're going to build an LS motor, especially for drifting or any kind of hard use, is we TIG weld the reluctor wheel with tack welds in a few places. Now in drift engines, we've seen time and time again the reluctor wheel spin and you lose your crank sync. That happens so often. So for a drift engine, you just about have to do it, and it's probably not a bad idea anytime you build an LS actually, because it's easy and it solves that once and for all. Some of the things you don't see, we use a fluid damper for a harmonic balancer. We really like fluid dampers. You know, they're kind of amplitude sensitive, and they're not so, you know, like in tune to like one frequency, so they work across a wide range of RPM, and the more the torsional whip, the harder they work. So we usually use fluid dampers on engines like this. I guess that's about it. You've seen almost all of it. Maybe ARP studs holding the heads down. When we align bore and machine the blocks, we use a torque plate, try to get the block hot. We use the studs, so the higher torque distorts the cylinder wall in the same way. If you use stock head bolts and torque plates, it doesn't distort quite the same. You don't get good leak down. What other little tricks do we do that I'm willing to talk about? That's about it. But if you want a high horsepower, really durable engine that'll put up with the hardest abuse, this is something like what we would do for your racing class or whatever your rules are. We can tailor it to whatever your needs are. We can make more power. You know, it's just a matter of what your specifics are. If you'd like us to build your LS, go to MotoIQ.com, click on Garage Services, and we'll get back to you. Thanks for watching, and don't forget to subscribe if you like this video.